Okay, welcome to this will be lecture number 7, I guess. The first 6 lectures videos, what we have seen is basically some introduction. We looked at the wave characteristics in a general fashion and specifically for sound waves. And we spent a lot of time on how to measure or characterize the sound waves. The two important things are amplitude and frequency. We showed those two are very important characteristics as far as the sound is concerned or noise is concerned. And then we looked at how to measure that using microphones, a sound level meter, the processing of the sound that is acquired in the form of octave or 1/3 octave bands, because the human ear tends to process in that fashion. Weighting functions, all of these we have gone through. And of course then we looked at basically some metrics which are more from community noise perspective, noise rating, noise criteria, loudness, which is a perception based index, phones and so on. So all of these, both quantitative and qualitative, are very important. Those things you should be familiar with from an industry perspective. Now we move from that into the mathematical part of this. So what governs the sound propagation? So this is governed by what is called as the wave equation. So the way the sound propagates in air is governed by this. We are going to pay attention to that wave equation. We're going to derive and look at solutions to this. There are various types of solutions that are possible, and we'll look at in what scenario what type of solutions is valid, right? So the wave equation derivation. So earlier we start off by, I would like you to recall that the sound waves are basically longitudinal waves, right? So what means is, of course, we'll again put up the animation. So what it means is that the air particles are basically going to move back and forth along parallel to the direction of wave energy propagation of the wave. So this is the animation that you saw earlier. So you can see the red dots basically, or the black dots, whichever. The red dot is so that you can focus on one of those particles. So this is a like excitation. As I remarked at that time, you could think of a speaker diaphragm which is back and forth and is pushing the air particles in front of it. Those air particles in turn transfer the energy to the neighbors, and then it propagates and comes to your ear even though you are sitting a few yards away. So another important, in order to transfer that energy, you require a medium. So sound waves will not travel in vacuum. This is something that you should be aware of. Unlike electromagnetic waves, a medium. So if there is no medium, then there is no sound waves that will basically travel. Sound wave is a longitudinal wave. You can focus on one of the red particles and you can see that it moves to the right and then comes back to the left once that ends. So that in mind. Alright. Again, this is the second thing that I showed you with an arrow there to show that the wave keeps propagating. The black arrow corresponds to the wave going, and you can see the particle motion. The red arrow is kind of going left to right, and the wave is going from left all the way to the right. So the wave is kind of propagating all the way down, right? So anyway, so these saw earlier. Now the idea is, how can I write some mathematics which governs this behavior, right? So what are the things that come into the picture? So we saw already the quantity that we were measuring is acoustic pressure. Remember, acoustic pressure is basically the pressure fluctuations over and above the atmospheric pressure. So there is a mean atmospheric pressure, and when I speak, I am creating disturbances which generate pressure fluctuations which are over and above the atmospheric pressure. So this is what we were measuring through the microphones. So acoustic pressure is a very important quantity that is the easiest to measure. So we have been measuring that quantity. As you saw that there is in the animation, you saw that there is local fluctuations. The particle keeps moving back and forth. So there is a velocity associated with the particle displacement, of course. The position changes, but you also have a velocity acceleration associated with that. So the kinematics of the particle movement. So pressure is something that is created because if you go back, let's focus on this. You can see that as the wave propagates, you can see dense particles, and then the particles kind of move away So the denser regions, the pressures basically will be what we call as compression happening. So therefore pressure will be larger, compressive pressure. When then the particles kind of expand, so you have what is called as a rarefaction or an expansion. So the pressure fluctuations, so the compression basically pressure by, we call positive pressure basically as compression. So if I say pressure is 0.1 pascals, then that means I have a compression of 0.1 pascals. And if I say minus 0.1 pascals, that means it has gone below the atmospheric pressure by pascals. So there is an expansion, local expansion that is taking place, right? Obviously these are not very large expansion in the compressions that are taking place, so keep that in mind. So these, you can see what is called as a little bit later. So these, if you just step back and see that, you can see lines which are progressing. Denser parts of it is the compressive compression of the air particles, then they expand and then they get squished together and expand, and the whole thing keeps moving, called as a wavefront. All right, so therefore so pressure is important. There is a particle velocity, we are saying particle velocity, but please remember there is a displacement and an acceleration associated with that. There are local changes to density. So when I compress the air and then I expand the air, there are going to be changes to this density, right? The air density, of course you have a mean density, and then there are perturbations about that density, because I'm going to compress it locally, so there is going to be an increase in density, and when I expand there is going to be a decrease in density. So the buildup of pressure up and down also creates a density fluctuation, so that is also happening. There are also temperature changes with compression and rarefaction. So we will get to this, of course we are not talking about obviously if the temperature changes are not very large, because if it was, then you will feel the temperature changes. So obviously we are not going to create 10-degree increase by just speaking. Fortunately that doesn't happen, otherwise you have a room full of people speaking, then suddenly the temperature cranks up by 20 degrees and it becomes very uncomfortable. So we are talking about small temperature changes. We will look at the model that mimics and how we will be able to calculate this temperature change. So this is something normally we don't worry about in acoustics per se, although this does happen. The changes are not very large, but it does happen. So you have basically the kind of quantities that come into play are one, the acoustic pressure, which is the fluctuation over and above the mean. You have particle velocity. You could also consider kinematic quantities such as displacement, but normally in acoustics we are more worried about the velocity of the particle. The density changes due to the pressure fluctuations, and of course again the pressure fluctuations creating temperature changes. So these are the four variables. They are not all independent. We will see that there are relations governing these variables. So whenever we build a mathematical model, we have to make assumptions. You have seen this right through as you have gone along. We make you can't build a model for exact reality, so we kind of dumb it down, if you want to call it, or we'll say we'll make some assumptions. Now of course how reasonable these assumptions are comes from observations that we make with the math model, and then verify that with reality. If it's reasonably close, and we are engineers, please keep that in mind, then effectively these assumptions are a fair bit are reasonable, right? So the first assumption is that the fluid, which is in our case air, we treat this as an ideal gas. So this comes from thermodynamics. We call that as an ideal gas. We also say it is perfectly elastic, right? So, and then of course if you are wondering how come air is elastic, just think about it, and these are things that you have to ponder about as to why I am calling that as elastic. What do I mean by perfectly elastic? Of course what it means is that if I apply a load and then remove the load, I go back to the same configuration. There is no residual displacement of air particles, or so it goes back to its original configuration. So I take something and then I compress, and then when I come back to the original pressure level, then effectively everything goes back to where it was. So that's what we mean by perfectly elastic. Remember, I am not saying it is linear, I am only saying it is perfectly elastic. So often people confuse. When I say elastic, your mind kind of thinks it is linear. It need not be. All that it means is that if I apply a load and then remove the load, it comes back to its original state. So that's what we mean by elastic, right? We also make some simplifications such as homogeneity. That means the properties that we are talking about, density, temperature, etc., is basically direction independent at a location. It of course varies from location to location, but if I look at a particular location and look around in various directions, then effectively the properties are direction independent. So that's what we mean by homogeneous and isotropic. We also neglect viscous effects in acoustics, at least for the class of problems that we are interested in. So we assume it is inviscid, which means basically we are neglecting the viscous effects. The process, the temperature, we talked about a temperature. So temperature, when we talk about a temperature, we have to associate a certain process with this. It is an adiabatic process. I would like to remark here that in fact the great Newton, who had done quite a few things, got it wrong in acoustics. He said this business of compression and rarefaction was an isothermal process. Of course, in thermodynamics you have come across both isothermal and adiabatic process. So adiabatic process simply means that there is no heat transfer, right? So whenever that compression happens in that particular small volume that I am looking at, there is no net heat flux that gets transferred out of that box, imaginary box. So it's an adiabatic process. If it is isothermal, I have to have heat transfer so that the temperature equalizes, right? And what we are going to ride on top of all this, so we said fluid is ideal gas, perfectly plastic, homogeneous, isotropic, inviscid, so many assumptions we have made. And we are going to an adiabatic process, which, as I said, Newton made the assumption that is isothermal. We'll see why he was wrong. Obviously, as I said, the test of any model is a measurement, and if the measurement doesn't match the model, then of course, assuming that you have done the measurement correctly, you could be wrong with measurements. See, often people think, there's a joke that is that goes around that when an analyst, many of you will do simulations, finite element simulations. Usually nobody other than the guy who did the simulations will trust the results. So you go sit in a meeting, people will bombard you with a lot of questions left and right, doubting your finite element analysis. So this is generally true of simulated results. But interestingly, if it is some measurement, everybody assumes, the guys to whom it is being presented assume that it is the God-given truth. While the guy who has actually made the measurement knows that there are a lot of uncertainties in the measurement and the measurement itself could be wrong. So this is unfortunately the way world works. So not all experiments are correct and not all simulations are wrong, right? So if done carefully, both can be fairly accurate. Okay. The other thing that we assume is that these acoustic variables, that means the pressure fluctuations that we saw. See, please remember that already we saw some numbers, right, in terms of amplitudes for the acoustic variables. In terms of the amplitudes, we saw that it can range from 20 micropascals to about 10 pascals. That in relation to the mean atmospheric pressure, which is 100 kilopascals, is obviously very small, right? Small variation around that value. So density fluctuations about the mean value is also going to be small. Velocity, particle velocities are going to be small. Remember, they are moving back and forth. It's not like I have 100 meters per second, because if I have the sound wave coming and hitting my skin at 100 meters per second, the real airflow you will be able to feel. So there's no such velocity of that magnitude. So therefore, most of the acoustic variables, so the acoustic particle velocity, acoustic pressure fluctuations, acoustic density fluctuations, as well as acoustic thermal fluctuations are all small. Therefore, we will be able to use a linear model. So up to this point, no linearity was assumed. At this point, we are going to impose the fact that we want linear behavior. What do we mean by linear model? So obviously, when you say a system is linear, please remember the principle of superposition holds, right? So that is one of the major properties of linearity, that if I have a solution A and a solution B, alpha A plus beta B is also a solution which is acceptable, which is what is called as a superposition principle. So linear model affords that. So okay, all right. So essentially these are the assumptions. This is very important to keep these in the back of your mind. There are situations where this will not be true. One of the classic examples is what is called as a supersonic shock wave, right? So for example, when a plane breaks the sound barrier, So you have these military aircraft today. There's commercial aircraft, the Concorde is dead, but you have military aircraft which can fly above 1 Mach. So when they break the sound barrier, which is 1 Mach, you will see a shock wave that is generated in the atmosphere, and that propagates. So in the near field of that shock wave, a lot of these things are violated, and so you have to study that considerably differently. But we are not going to do any kind of aerodynamic noise in this course, at least the kind of shock waves that we are talking about. So for whatever we are going to do, these assumptions are reasonably valid. All right. So let us look at the derivation quickly. So the derivation basically hinges on three things, and this you will find across fluid mechanics, across many fields. Basically the conservation laws are what we are going to go through. So if you remember your fluid mechanics derivation, or even solid mechanics derivation, solid mechanics mass conservation is kind of implicit, but the three things that we are going to do. So if you look at the derivations, we talk about mass conservation and momentum conservation, and in fluid mechanics you also have energy conservation. So these three. So if you look at mass and momentum, the variables that you typically will look at is of course density, pressure. Momentum of course will come up with pressure, well, acceleration obviously, because we are talking about momentum, change in velocity. So velocity, pressure is associated with momentum. Mass conservation is associated with again particle velocity as well as densities. And of course the energy, when you look at energy, temperature will definitely come in. But in our case we are going to only focus on these two, the mass conservation part and the momentum conservation part. So these are the things that we are going to focus on. So let's look at the derivation. Basically proceeds, we are going to take a small infinitesimal cuboid in space, in air, and there are particles inside this, and what happens is that now I have an acoustic wave coming in. What is shown is only the x direction in the picture. I have acoustic flow coming through this. I will use flow, but in reality it is not flow in the sense of having a mean velocity. Of course you can have an acoustic wave traveling with mean flow, but we are not worried about mean flow here. So this is purely acoustic flow. So the acoustic energy is entering this box, flowing into the box, and I'm showing only the x direction. So you can see that dy dz is the infinitesimal area through which that flow happens. Rho ux is basically, ux is the particle velocity component along the x direction. Rho times u x basically is multiplied by the area, gives me the mass flow in. So this is what is coming in. So what is going out is rho ua at x plus dx, and we do a Taylor series expansion. And when you do that, and again I would urge you to go sit and derive this, what will be left with the Taylor series expansion is that you will have the net flow. So the what is coming in is rho ux into dy dz. Obviously dy dz is the infinitesimal area across which it is flowing. On the other side I have rho ux plus the Taylor series expansion will give me dou by dou x of rho ux. Remember that dy dz doesn't change, whereas the density and the density as well as the particle velocity changes from location to location. At a particular location it is homogeneous. So in that area, if I measure, what we have assumed is that it will always be rho u irrespective of where I measure on that dy dz. But obviously from location to location it is going to change. These variables will have different values at different locations. Alright, so therefore the net outflow will be dou by dou x of rho ux. Remember I have not pulled the rho outside. I am not assuming it is constant. I am assuming that also changes. Density changes are also there. Times dx dy dz, which is the total volume of this infinitesimal box that we have considered. So I have the acoustic energy coming. Of course it's going to come in all directions. So I have just shown the x direction here. In the next slide we will do the other direction. So if I do the other two directions, so I have x, and similarly I'll have y, and then I pointed the z direction, and similarly I'll have the y direction. So if I sum up all of these things, then effectively I will have three terms, right? So the three terms that are going to be there are dou rho ux by dou x, dou rho uy by dou y, and dou rho uz by dou z, multiplying this infinitesimal volume. Okay, now there is mass accumulation in the volume. The mass accumulation, that is, so this is classic fluid mechanics mass conservation that you write, right? Mass flow in, mass flow out, the difference should basically be the mass that is accumulated inside, right? Of course, if it is removed, then it is a negative quantity. If it is increased, then it is a positive quantity. Now, the rate of increase of that, the mass accumulation is given by density change with time, dou rho by dou t multiplied by the volume. Rho into V is the mass. So, effectively, this is like a dm by dt statement, right? So, this is the rate at which the mass is increasing in the infinitesimal volume. Now, of course, I have written a one-dimensional box here, that as though the mass conservation. So if you look at this, I have written it only with one term. Strictly, as I told you, there are you can have along the z direction, you can have mass flow in and out. You can also have along the y direction mass flow in and out, right? So we are going to limit, so this, of course, I have just shown one direction, so you can generalize this. This is what we will do in the next slide. So if we extend this argument to 3 dimensions, then the mass flow out in the y direction will be this, mass flow out in the z direction will be this, and therefore the net outflow is given by this should equal the negative of the mass accumulation, right? Because if you say that there is a net outflow, that means the mass has been removed from that. So if you look at this is the net outflow from the infinitesimal volume, that is equal to minus dou rho by dou t. So this equation is basically the mass conservation equation, dou rho by dou t plus divergence of rho u. So this is equal to 0. Now, in fluid mechanics, you would have studied steady flow. That means density doesn't change with time. Steady means properties don't change with time. So that is what we mean by steady flow. So if it is a steady flow, as you will see in fluid mechanics, this term would go to 0, and then you have the classic divergence, which is basically del dot rho u equal to 0. Divergence of rho u equal to 0 is your classic mass conservation equation that you have. So therefore, there are parallels to the fluid mechanics case. So exactly the same thing that we have here. So in the case of rho being 0, which is not true in the acoustic case, obviously if rho, remember that this rho has a mean component plus a fluctuation component. That fluctuation component cannot be 0, which means basically there is no acoustic energy. So unlike your classical steady flow equation where divergence of rho u is 0, we don't have that equivalent here. We will always have this dou rho by dou t. We will come back to look at this. So I think this is a good point place to stop this lecture. So what we have done is we have set up, we are trying to derive the wave equation that governs propagation of sound waves in air in any fluid, but our focus is going to be basically on air. A lot of the things that we will derive will basically be with respect to air as a medium. And what we have done is we have listed out a certain, we identified what are the kind of variables that are involved: acoustic pressure, acoustic particle velocity, or could be displacement. Then the other variables, density fluctuations, which is related to the pressure, and of course temperature, thermal. We showed that we have made an assumption that it is adiabatic. A little bit down the line, I will show how experimental measurements basically proved that the adiabatic assumption is more accurate than an isothermal assumption. So remember, Newton assumed it was isothermal and was proved to be wrong. So we will see that subsequently. Therefore, so at this point, what we have done is, remember that to derive this wave equation, we are simply going to use two conservation laws. One is conservation of mass, which we have derived now. So the boxed green equation is basically a statement of conservation of mass. We will then look at the conservation of momentum, and then obviously instead of an energy equation, we are going to use the fact that, so we will now come to the thermodynamic process, which we have assumed to be adiabatic. So that will be used instead of the energy equation to basically arrive at the wave equation. So in the next lecture, we will proceed from this point forward. We will see the other momentum conservation as well as the adiabatic process come into the picture, and using that and through some mathematical jugglery, we will arrive at basically the equation governing the propagation of sound in air primarily, though this is generally true for most fluids. Okay, we will stop here. So we will continue with this in the next lecture.